This video is about errors and the different errors that are made during simulations, and what you can learn out of them, and also how you can debug them, because errors are very important for us to learn. And if you're doing something new, you will make errors. And let's see what were the different things that we learned while doing that. Okay, so this is sort of going to be the pattern of this video. We'll have a schematic, we'll have an output, and we'll try to make sense of it. And then we'll figure out what went wrong and what could have been fixed. So you can pause the video if you want to look at the schematic. So there's a schematic and the output looks like a bar. So in this case, what has happened is that the transient time has been set to 1 second. That's a very long time if your period is only 20 microseconds. So what you're getting is actually a whole lot of periods, and you can't really make out what the output is at this zoom resolution. However, if you zoom in, this is a left click, there are actually two waveforms, and one of them is your square wave and the other one is your triangular wave. So keep in mind what is the length of time you are simulating versus the period that you expect from the circuit. How about this example? So in this example, if you look at the schematic, you can see that there's nothing connected here, it's floating. It's very rare that you're going to have circuits in which you'll have pins that are floating and still everything works okay. So let's see what we get out of this. Okay, let's look at the output. Oh, that looks alright. Input first and then the output. And this looks okay. So what happened? So this brings an interesting property of simulators, and what the simulators do is any point that they find floating, they put a really large resistor, well, a very large resistor to ground. And what this means is if there is this floating net, it is possible that the floating net would be at ground, and that's why the simulation works. So one thing to note is just because you get the output waveforms doesn't necessarily mean that your circuit is kosher. I mean, it's fine. It means that you may still need to look at the circuit and some issue might show up later. Because if there's a very large resistor and there's something injecting current into it in a real model of an op-amp, then you might have a problem. Okay, so in this schematic, you can pause these videos and figure out what's wrong on your own. So the input looks fine. Input is going from -1 volt to +1 volt. It has an initial delay of 5 microseconds. It's okay. And it's switching back and forth. That looks fine. Let's look at the output. Okay, now that looks really strange. Okay, so what has happened here? This part actually does look like it's a part of a triangular waveform, and in fact it looks like it reaches its bottom point. The voltage is turned negative here, which means since it's an inverting amplifier, this is an inverting integrator. The current gets pumped in when this is positive, which means this voltage is more positive than this voltage. So the voltage is negative, so that's what is happening here. As long as my input was positive, it was +1, yeah. This is my 0. Now that the voltage has gone negative, this voltage is lower than 0, which is here, so the current is getting pumped in the other direction. Which means in this direction. Which means now the current is getting pumped this way, and the output voltage is actually becoming positive with respect to ground. I mean, it's discharging the capacitor first. So that's what's happening here. Well, this part. That seems okay. And then suddenly at this point the voltage is still negative, so it should have continued going, like that up, but it's sort of dying, which means it is getting connected to ground. The input voltage is at ground, so the output voltage is also going at ground. Hmm. Well, the capacitor can't do that. The only thing that can do that is a switch. If I short this node from here to here, well, okay, that makes sense, because initially I was supposed to have a switch that held this voltage at ground and then released it, but now the opposite happening. So this voltage source is flipped around. Okay, let's look at this circuit. Okay, let's see. Let's just plot the input. Okay, this is similar to what I had before. And let's plot the output. Okay, so the switch seems fine. It's interesting, there are some glitches here which we had not seen before, but the output is actually very small. Starting at 0, it's asymmetric, it's going up to 1 point, maybe 1.3, 1.4 volts, and it's going down to, this is 1.2, so 1.1 or so. So what's going on? So in such a case, when you're not getting the result that you expect, the first thing to examine is that, well, this is ground, that I know because it's physically connected to ground. This is supposed to be a virtual ground, so I should look at this. This voltage was supposed to be at ground. That's my input. This is the virtual ground. So the difference of this is what is getting integrated in the capacitor. The difference of this looks like some bit of a glitch, and then okay, so that must be actually the current flowing through the resistor, and that's what is being averaged, I mean basically accumulated by the capacitor. So that's the output I'm getting. So since this sort of looks like a square wave, you can't really tell that the glitch has a small area under it, so you can't really see that it affects the triangular wave much, but that's what we are saying now. So clearly the amplifier is all wrong. There's something really wrong with the amplifier. So the op amp that we should be using is, well, for initials at least, the universal amp. Universal op amp, at least for now. But this gives us a chance to look at what are the kind of op amps that are available. So this is a precision operational amplifier, so it's supposed to probably take very fine inputs and just be able to separate them out, but maybe not without too much gain. How about this one? Low noise, high speed precision amplifier. Okay. And how about this one? High speed operational amplifier. Maybe this would work, so let's try that out. So the nice thing about amplifiers is that you can plug and play them. So I don't want that, I delete that. Now let's run this up. Ooh. Okay, so let's see the input again. Okay, the input is a clean voltage source, and the output is a triangular wave. See, there is actually something happening here. There seems to be a lot of ripple and ringing, and we'll deal with these as we start understanding simulators and how they solve, and how to get better results than that. But for now, it may or may not be because the amplifier, and it may also be with the way LT Spice is simulating. But it's interesting to know that when you put realistic components, you're going to get results a little different from what you expect from ideal results. So first, it's good to understand the ideal results, and then we get into, is this really noise or is it really ringing, and so on and so forth. Yeah, so again, you can pause the video and see what's wrong. Let's see what's the input. It's a square wave, that's fine. What's the output? It's also a square wave. Whoa, what happened here? So I hope you pause the video and figured out what's wrong. And here what's gone wrong is the op-amp positive sign and negative sign, good night, have got flipped. Okay, I'm not putting you to sleep, I was just saying good night to Sundar who's going home. So the positive and negative signs are flipped. And now the question is, what is with the positive and negative signs with op-amps, and with the idea of a nullator and narrator, it should make no difference. So if you had a true nullator and narrator which has infinite gain, and this is exactly equal to 0, then it may not matter what sign of the op amp it has. However, if we have, even the universal op amp has some finite gain, and if you have a finite gain, it's more getting closer to a realistic op amp, then the plus and the minus signs do matter. And so the plus means if you have a small voltage here, delta V, then this delta V is getting multiplied by a gain A and coming out here from the plus to the minus. And this can either aid the way the input is coming, or it can it is basic yeah, it's either positive or negative feedback. So positive and negative feedback is a fairly important um, thing to learn, so I'll spend a video on that. But right now, if you look at it, if my input voltage initially is minus 1, it was minus 1, so the initial voltage, this one is minus 1 plus 1, it's moving, this is your input. But what's happened at the output is that the output is stuck at 10 volts. Now the switch is shorted out, so input is equal to output, and the output is now determining this node, and it sort of helps each other. This is positive, this is a large voltage with respect to this, it has a large gain, it stays at 10 volts. So these circuits will tend to get stuck in one state or the other unless they are forced to move from that state. So that's sort of what's happening. It woke up at minus 10 volts, helped itself, and then continued going to minus 10 volts, and it was stuck there. And you have to sort of force it. You have to, when you're switching here, you're sort of forcing it, and it almost follows your waveform. It's not going in the other direction or anything, it's almost following your waveform. You're pumping this node up, and at some point it charges the capacitor and switches it to the way you want it to be, and it sort of follows the waveform at the input. So you can actually use something like this when you want to get a square wave out of a signal that's not a square wave at its input, which interestingly is something you were doing towards the end of the class when you took an integrator and followed it up with something that you wanted to get a square wave out of. So we'll look at it then too. Some of you encountered this. So in this example, the input's fine, and the output is a waveform that's not symmetric. It's going up and down. So what's going on here? So what's going on here is that the time at which we are releasing is some 22 microseconds. So we started with 5 microseconds, and then you went up, and so you would expect this to be 20 microseconds plus 5 microseconds, so this is 25 microseconds. So you released it but you didn't release it right at the center. So when you released it here, it was able to accumulate, basically get the area. When I say accumulate, I'm talking about the area. It was able to get this much area, which was basically a small number, and then it subtracted this area. It's a much larger number, and then it sort of stayed there because this one equalized that one. But the initial area you got set your top point. It didn't get to 5 volts, it only got to 3 volts because your delay was off. So you can get various offsets depending on where you turn on this, or basically release the switch. So I encourage you to play with it and change the value and see what happens. What if I do 2 microseconds? So it gets released early, and that, yes, is very similar to 22 microseconds. What if I did 5 microseconds? My caps lock is on and it doesn't really care, so this is not case sensitive. Nice to know. Now it looks similar to what would have happened when you were releasing it exactly at the time where things switch, right? So it has the positive waveform first, so it averages that out, and since it's inverting here, the entire it goes up to the most negative point it can, and then it comes back, and so on and so forth. Okay, this is a really nice one. My input is a square wave and my output is a triangular wave, but it looks like it's going away. Okay, maybe I should simulate it for longer. Yes, it really is going away, isn't it? Don't worry about the capital, it still means 1 milli. It's basically saturating out. So what happened here? So clearly there's something going on, and one way to figure this out is to look at the input. Okay, so let's think of what's happening. The result is accumulating up, which means and this is a ramp. This is an integrator. So a square, if a DC integrates into a ramp, so there must be a DC in the input that's making the inputs or output sort of ramp up, and then of course it gets stuck at 10 volts. That part we know. Once it gets stuck, it just keeps going back and forth. It can't cross 10 volts because my input supply is 10 volts. It can't cross the supply. If you have a realistic op amp, it won't be able to cross the supply minus 1 volt or something like that. Okay, so there must be a DC component in the input. So one way of getting rid of many waveforms is to click on the waveform you're interested in twice. So we do that, and for this waveform, if you do control and left click, you get the average value, and you can see it's got a 10 millivolt average value, and that's what's making the output drift. So if you put a small input DC voltage here, it will keep ramping the output till it saturates eventually. So that's what's happening. Interesting. And why is it that we have a small DC component? And I'm sure you figured that out by now. It's because something's wrong with an input statement. So let's see what this statement is saying. Ouch. So we have a -1, check, that's okay, to +1, that's also okay, 5 microsecond on time, that's this one, and 20.2 microsecond. Okay, wait. So this is not, oh sorry, 5 microseconds was the delay, that's this one. That's 5 microseconds, this is 10 microseconds, and the period is 20.2. Why was the period 20.2 again? Well, the reason was that I had the rise and fall time earlier of 0.1 microsecond. So if I take 0.1 microsecond to rise and 0.1 microsecond to fall, then if I want the part that's high to be exactly the part that's low, then you need to subtract the rise and a fall time from it. The next period again starts here, so you don't have to consider the next period. So that's why I had added a little bit more, zero point 0.2. And if I hadn't added that, if I had said 10, 20 micro, 10 micro, and I had put zero point 0.1 microseconds for rise and fall, I would have had a different problem. So let's look at that. So let's change it. We made the rise and fall time very very small. A nano is 10 power minus 9, so much smaller, 10,000 times smaller than a micro. 0.1 microsecond. Okay, I'm going to remove the caps, it's bothering me now. No, yeah, there we go. And I said, my on time is 10 microseconds, so my period should just be 20 microseconds, and that should give me 50-50. So if I did that, and okay, let it simulate. Now the waveform still looks fine, but if I look at the average value, now it tells me, you have a 10 millivolt average value on the positive side. So if you've figured everything out so far, it means the voltage should ramp down because it's inverting, right? So, and it does. The voltage ramps down to minus 10 volts. Interesting. And the last one, input. Okay, output. Oh. Okay, what happened here? My input was chopping along and something happened. Is it the switch? Is it a switch? Something the switch is doing? No, that doesn't look right. The switch isn't doing anything there. Well, in fact, it can't do anything there. It's a voltage source. So the only way the voltage source can stop working, not doing what it's supposed to, is if we have asked it to do something different. So let's look at what we asked it to do. That last 5, the rest is fine, is the number of cycles. You asked for only 5 cycles, so it gave you 5 cycles and stopped. So if there's an option you don't understand, you can just leave it. And now it is what you expect it to do. Okay,